agree to be.
Yes. Go ahead.
So welcome everyone to the first Origins Colloquium of 2025. It's a pleasure to introduce Susana Lozano to give the talk this week. Susana received her bachelor's degree in physics at UNAM in Mexico, before then moving to UC Berkeley, where she did her PhD with Frank Xu, graduating in 1988. She was a postdoctoral researcher at Arcetri Observatory in Florence for a few years after that, before returning to Mexico to join UNAM at the Institute of Astronomy. In the 1986 here, you moved to UNAM Morelia campus to basically set up a whole new institute there, the Radio Astronomy and Astrophysics Center, of which you were academic secretary and then later a director. And now there's in the center, there's close to 30 researchers working on astrophysics. So Susana has won a number of awards, including the Guggenheim Fellowship, and is also a member of the Mexican Academy of Sciences and the Mexican Physics Society. So we welcome you, Susana, to tell us about your work on magnetized protoplanetary disks.
Thank you, Jonathan. I'm very happy to be here in this colloquium. And today I'm going to talk about magnetized protoplanetary disks. If at any time there's a problem with the connection, please let me know. So first, I will start talking about the morphology of magnetic field in molecular clouds. On the left-hand side, you can see one example where there's a very large-scale magnetic field, which shows an ordered structure shown by the gray lines. And this magnetic field is perpendicular to large gas filaments of the order of tens of parsecs, where the star formation is occurring. So at large scales, the magnetic fields seem to be perpendicular to the gas, but then, as shown on the right, by Pillai and collaborators, the relative direction between the magnetic field and the gas filaments changes from perpendicular at low extinctions, and it becomes inside the filament parallel. The magnetic field direction is parallel to the gas, to the filament. So if you look at smaller scales, at the scales of dense cores down in this slide, the polarization vectors show the direction of the magnetic field in the green arrow, the green lines, and you can see what is called the hourglass morphology. That is a signature of the magnetic field being dragged during the collapse. So you can estimate, as we will see later, the strength of the magnetic field using these polarization vectors, which gives around 640 microgauss at this scale. So the magnetic field strength is measured with several techniques, mainly the Zeeman effect that gives the magnetic field along the line of sight, and the DAS polarized emission, as I just showed you, together with the Davis, Chandrasekhar, and Fermi method that can give you an estimate of the strength of the magnetic field in the plane of the sky. So here you see on the right, the magnetic fields at different densities. They range from tens of microgauss to thousands of microgauss. And as the density increases, and the lower panel shows that these measurements correspond to different objects on the sky. So the importance of the magnetic field relative to gravity is given by the mass-to-flux ratio here on the left, that has this ratio that we call lambda. It has to be larger than 1 for gravity to win and have gravitational collapse. And as I showed before, during the gravitational collapse, the magnetic field is dragged into the dense cores. So from Zeeman splitting measurements, one gets, as I said, from tens to hundreds of microgauss at densities from 10 to the 3 to 10 to the 4 to the 10 to the 5 in molecular clouds. These are several measurements through the years, and here you see an estimate of this mass to flux ratio as a function of column density in logarithm. And you can see that it is around the values of 1. And after corrections for the geometry of the clouds, the values that one gets for magnetized cores, the dense regions where stars form, is between 1 and 4. And this is what is called subcritical clouds. You have to have supercritical clouds. You have to have supercritical clouds for collapse. So what happens when a magnetized core collapses if you don't include rotation? Gali and Xu predicted that the magnetic field lines would deflect, the Lorentz force would deflect the gas towards the midplane, creating a flattened structure, as you see here on the right, numerical simulations of Allen, Li, and Xu. And you see the flattened structure that is called the pseudodisk, and it's called pseudodisk because it's not in equilibrium. The material is flattened, but it's still radially accreting to the center. So the field lines, which are shown here by the solid lines, show the hourglass morphology and the flattened structure, which is the pseudodisk. But then molecular clouds are rotating, and so what happens when rotation is included? And so the naive expectation was that the magnetic field lines would deflect the gas towards the pseudodisk at a large scale, and this would continue to collapse towards the center, conserving angular momentum and creating in the center a small rotationally supported accretion disk. Nevertheless, in ideal MHD simulations, which means that the magnetic field is coupled to the gas, they didn't find any rotationally supported disk, and this was due to the magnetic braking. So if you, here I show some simulations of Fromank et al. And on the top panels, these are simulations without magnetic fields, which correspond to a mass-to-flux ratio of infinity. And you can see from the top view that you form a disk, and on the side view, you form a small centrifugally supported disk. Nevertheless, if the simulations that the magnetic field is included at levels of magnetization, here I said lambda, put lambda equal to 2, that is observed in molecular clouds, there's no rotationally supported disk. Only in the side view, you can see a flattened structure that is still collapsing, that it corresponds to the pseudodisk. So the reason for this not forming the disks, the rotationally supported disk, is what is called the catastrophic magnetic braking. And this it happens because during the collapse, if the field is frozen to the gas, it will form what is called a split monopole configuration, where the field lines on the below the midplane go into the center and diverge above the midplane. And if you examine the torque equation, you can see that the gas is being torqued by the magnetic tension, and then the field diverges because of this split manifold configurations, but the rotational speed or the azimuthal speed goes to 0. It has a positive exponent at low values of the radius. So if you look at the on the left, the field lines are the straight lines here that form this split monopole configuration, And these contours show the flattening of the gas. And on the right, you can see the behavior of the azimuthal speed that at large distances from the center, it goes like r to the -1, conserving angular momentum. And instead of continuing this behavior towards the center to achieve the Keplerian rotation, to switch to Keplerian rotation, sorry, the azimuthal velocity is braked and it even becomes negative, so you have counter rotation. So the magnetic braking is catastrophic because the field is assumed to be frozen to the gas. Of course, this is not the case at high densities, because if you look at the evolution of the magnetic field, there are several dissipation effects. One is the first one that corresponds to the ohmic resistivity, and this is because the ions and electrons are knocked off by collisions from different field lines. And the other effect is the Hall effect that happens because the electrons and ions move differently under electromagnetic fields and collisions. And then the third effect is the ambipolar diffusion effect that is due to the fact that the magnetic field is attached to the ionized matter and not to the neutrals, and the neutrals only feel the Lorentz forces through collisions. So when you include the non-ideal effects and the gravitational collapse that include all these processes, require enhanced resistivities. And for all three effects, I mean, there have been many simulations during the years, and of course, this is not a complete list. And one way of enhancing these resistivities is by the removal of small dust grains or by dust growth. So in both cases, the resistivities are lowered and then, are increased, and then this means that the field is decoupled from the gas. So here on the right-hand side, and on the left, you see like the simulation forming a rotationally supported disk, and by Krasnopolsky and collaborators. And on the right, you see the behavior of the rotational speed. As you go to the center in this direction, the rotation finally acquires the Keplerian profile. So this is not the only way that you can prevent this magnetic braking. Other alternative solutions were proposed, like the misalignment between the magnetic field and the axis of rotation, because this would reduce the braking, magnetic braking. Another way of reducing the magnetic braking was because the magnetic field is attached to the envelope. If the envelope is depleted, then the disk could grow with time at later times. Another possibility was that the turbulence enhances the rate of field reconnection and diffusion. This is the work done by the group of Siegfried and Santos Lima and Alex Lazarian. But it seems that this turbulent reconnection is not the main effect that happens in the simulations. And then another possibility is the expulsion of the magnetic flux in the inner region, where the ionization fraction is so small that the field decouples from the gas. And then there can be an interchange instability that really evacuates the inner region from magnetic flux. And this was proposed very early by Lee and McKee and followed by many other simulations. So anyway, disks are formed, of course, and we would like to know what is the magnetic field at the scale of protoplanetary disks. And if one looks at non-ideal MHD simulations of the collapse of magnetized cores to form disks, one can estimate different values of the mass-to-flux ratio, and this is not explicitly done in the papers, but you can get the information from the level of magnetic field and density conditions. And this can be large, like this value of 54, to lower values by a later work of Su and collaborations. And here on the left, this is the collapse of a magnetized torrent core, and you can see that magnetized sheets, dense sheets, fit mass and angular momentum to the central system of star and disk. And this is related to what the observers have called streamers, where the collapse is not homogeneous and axisymmetric, but can be, I mean, these structures are observed in many simulations and now in the observations. From the observational side, as I said before, one can get the direction of the magnetic field with polarization measurements of dust emission, and estimate the strength with the Chandrasekhar, the Davis-Chandrasekhar and Fermi method that calculates the distortion of the magnetic field due to non-thermal motions. And this method has been, many improvements have been added to take into account effects like, for example, the integration along the line of sight. And you can see a review by Patel. And on the other way is a direct measurement of the magnetic field by circular polarization in molecular lines by Zeeman splitting. And this gives the magnitude of the direction and magnitude of the magnetic field along the line of sight. And recently there have been a measurement of what the Goldreich-Kilafis effect, which is a linear polarization in rotational levels of molecular lines. But this is something that might, is just starting to be observed. And so the easiest is to measure the polarization of the dust emission. And this was, I mean, we all had high expectations when ALMA started to operate. But nevertheless, what Kataoka showed already 10 years ago is that the scattering coefficients, which are shown here by the dotted lines for different, for example, for large grains, for here, the blue line, and for, this is for 100 micron grains is the blue line, and here is the red line is for the small grains of 1 micron. But you can see that the absorption coefficients, which are the solid lines, are of the same, are smaller than the scattering coefficients. That means that the dust self-scattering dominates the polarized dust emission. And they propose that because the polarization is very sensitive to the grain size, so observing at different frequencies, one could obtain the size of the grains in the disks. Another effect is that the grains could be aligned not perpendicular to the magnetic field, but perpendicular to the radiation flux. And you have a star in the center of the disk, and there's an anisotropy in the radiation field. So the grains are aligned perpendicular to this radiation flux, and it's not due to the magnetic field. So, for example, this means that the polarization, what has been found in many studies now, is that the polarization of the dust emission changes with wavelength. Here you see recent work in HL tau from 7 millimeter in all the ALMA wavelengths to 870 microns. And so at the longer wavelengths, the grains are aligned perpendicular to the radiation flux. And at the highest frequencies, the grains are aligned by scattering by parallel to the disk minor axis. So this it seemed that this was not a good way of getting the magnetic field at the scale of the protoplanetary disks. But nevertheless, there are a few cases where they have argued that the polarization vectors do reflect the emission of grains which are perpendicular to the magnetic field. So this is the case of the object BHB07 11 by Alves et al., where here I show the orientation of the magnetic field that has an hourglass morphology. And also you see in the background the molecular emission that shows the blue shift and red shift emission from the gas in the disk. So they calculated a poloidal field of the order of 3 times the azimuthal field. Nevertheless, it has been argued recently that these polarization vectors, which I showed, these polarization vectors are rotated 90 degrees to give the direction of the magnetic field, but Guillet et al. Showed that for large grain, the polarization can be negative, which means that the polarization vectors are in the direction of the magnetic field. So this would show more a toroidal field instead of a poloidal field. So there are a few sources that show the magnetic field in the disk, but most of the emission of dust, polarized dust continuum emission is due to self-scattering. So we want to know what is the level of disk magnetization, because the magnetic field impacts the evolution and the emission of the protoplanetary disk. So as we said before, the parent core has values of the mass-to-flux ratio between 1 and 4. And one expects field dissipation. And as I showed from the simulations, one can obtain the mass-to-flux ratios between 6 and 60, for example. And we know that the protostar has very high values of the mass-to-flux ratio. And this was pointed out very early by Mestel and Spitzer, which implies that the flux from the cloud does not fall into the star. So the crucial question is how much flux is left in the disk. So now I'm going to talk about what is the effect of the magnetic field on the protoplanetary disks, and focusing on steady state models of magnetized accretion disk by Xu et al. And these disks that I show here, a cartoon, have mass accretion through a poloidal magnetic field, and they are subject to 2 diffusive processes: the viscosity that allows matter to accrete to the star, and the resistivity that allows the matter to slip through the magnetic field. And this one important effect, if you look at the radial force balance equation, you can see that centrifugal force is balanced not only by gravity, but by the effect of the magnetic tension. And this means that the rotation is going to be sub-keplerian. This effect can also happen, the sub-keplerianity can also happen if the thermal pressure is important in the disk. But so these poloidal fields that thread the disk that are supposed to be dragged from the dense core during the gravitational collapse provide a natural mechanism for the magneto-rotational instability that is a source of the anomalous viscosity that the disks need in order to accrete the observed accretion rates into the star. Now, the fact that the rotation is sub-keplerian implies that disk winds either need to have very fast diffusion across in the vertical direction, and therefore also in the radial direction. And this means that the material flows very fast to the star in very short time scales, or they need to be warm to overcome the potential barrier of this sub-keplerian rotation. Another effect that magnetic fields have on the dynamics of the protoplanetary disks is that it makes the planet migration faster. And the planets are moving at Keplerian speeds, but the gas is moving slower at sub-Keplerian speeds, either by magnetic field or by thermal pressure. But in the case of this magnetic field, poloidal magnetic field, one can calculate the loss of angular momentum and energy of the planet that produces the migration inward. So on down here on the left, we have a plot of the time of migration as a function of distance to the star. And the dotted line here calculates the type 1 migration only, that is due to thermal pressure in the disk. And the solid line is the migration due to a sub-Keplerian magnetized disk. So it happens faster than just with thermal pressure. And also it affects because it happens faster, it affects the amount of mass that the planetary core can accrete. And so it decreases this mass. And another effect is that it affects the stability of the magnetic field, the level of magnetization. The Tumbury parameter, which is this expression here, is modified by making instead of having the sound speed, and it's going to be the magnetosonic, it's modified by the magnetosonic speed, and the epicyclic frequency is going to be sub-Keplerian, because this is, the factor of sub-Keplerianity depends on the factor of sub-Keplerianity. And also the gravity is going to be modified by magnetic tension. It's going to be diluted according to the mass-to-flux ratio. So there are two competing effects. If the magnetic field enforces, makes this F value small, makes the disk very sub-Keplerian, then it decreases the stability. This modified Tumbury parameter decreases, but the magnetic tension down here and the pressure on the numerator increase the value of the Tumbury parameter. So altogether, one can show that the disks become more stable than the non-magnetized disks. So now let me go to the emission of the disks, of magnetized disks. One takes the models of magnetized disks from Xu et al. These models allow power law solutions for the magnetic field strength, the column density, the viscosity, where the inverse of the Prandtl number, which is the resistivity over the viscosity, is of the order of the scale height, so it's very small. So one can find the vertical structure of these magnetized disk models, and this has been done taking into account that the disks are subject to irradiation by the central star and viscous and resistive heating. So the bottom line is that there are different mechanisms that dominate in the midplane. For low mass stars, viscous heating seems to be dominant. For FURE disk, resistive heating dominates, and in the case of the third disks, the stellar irradiation dominates. So we're going to see how these models of the vertical structure and emission of these magnetized disks help constrain the values of the mass-to-flux ratio in the disks. Just before, let me show you here the examples of these models. These are the height and the radius for different type of models, that they all have an atmosphere which is heated by the star, and they have a central region, the mid-plane region, that is heated by viscous and resistive heating. So one effect that this magnetic field has is that the magnetized disks can be very compressed depending on the mass-to-flux ratio. Here I show the height, which is only 1 AU, and here, down here, the scale height is 10 times larger. So the aspect ratio of the disk, which is measured to be around 0.1, the height divided by the radius, is more in agreement with larger values of the mass-to-flux ratio. Another thing that you can find here are temperature profiles as a function of distance for different values of the mass-to-flux ratio. And these are vertical profiles down here as a function of height. So the temperature profiles show the inversion and the temperature inversion in the surface. This is the surface. But if you compare the height of a different radius, you are going to see that the disks are more compressed, as I said before, with when they are highly magnetized, with mass-to-flux ratios of the order of 4, and they are less compressed when the mass-to-flux ratio goes to 24. So the disks are hotter and more compressed. Sorry, they are hotter and less compressed for larger values of the mass-to-flux ratio. And so if you look at emission at 7 millimeters and the radial profiles for different values of lambda from 4 to 12 to 24, so more magnetized and less magnetized, you see that the disks emit more at when they are less magnetized, and this corresponds to this line corresponds to the opacity at 7 millimeters. So the emission increases with the mass-to-flux ratio of the system. In comparison with observed sources, in the case of HL tau, the upper panel shows the emission at different wavelengths, the radial profiles from 1 to 100 AU of this disk, and the orange line corresponds to 7 millimeters, and the frequency increases up to 870 millimeters microns, sorry, for the purple line, and so modeling this source implies that one can get from these models of vertical structure enough emission at 7 millimeters, which is hard to get if you have large grains of the order, the maximum grain size of the order of 1 centimeter. But the important, what I want to point out is that this disk can be modeled with a large value of the mass-to-flux ratio. It's not possible to use very highly magnetized models to get the right level of emission in this disk HL tau.
Maybe 5 minutes, Susanna?
Yes. Hello? Can you?
Yeah, that would be great. Then we'd have time for discussion.
Okay. Do you want me to stop, or you want me?
If you're almost done, that's great.
Okay. So finally, I think there are a few measurements of magnetic fields. Actually, there's one measurement of the magnetic field in the system FU Orionis, which by Donati, who measured a magnetic field around 1 kilogauss at 0.05 AUs. And he also inferred sub-keplerian rotation in the disk. But this is the only measurement obtained by spectropolarimeter or polarimetry or Zeeman splitting. Instead, with ALMA, that is now able to measure circular polarization of the CN molecule, there are only 2 upper limits, one in TW Hydra and another one in the system AS 209. And you can see the level of emission is at different wavelengths, from 900 microns to 3.1 millimeters. That one can get the level of emission for different models of this disk, but the disks have to be have to have a very low, very high mass-to-flux ratio, and it's so high that for these models one has to include the thermal pressure, not ignore the thermal pressure as in the models of Xu et al. So the thermal pressure was included in a very simple way with the beta parameter, which is the ratio of the thermal pressure to the magnetic pressure. So anyway, the emission of these disks, in the case of TW Hydra and HL tau, require large values of the mass-to-flux ratio. I'm going to go quickly just to say that, of course, the caveats of what I just told you is that one has to analyze the coupling between magnetic field and gas, because of the resistive processes that I mentioned before, the ohmic dissipation and nonpolar diffusion. One can calculate these resistivities and see if the plasma is coupled to the gas, or with the antipolar diffusion resistivity, if the ions and neutrals are coupled. So you need the magnetic field to be coupled to the gas to be able to produce all these effects. And of course, there are inner regions at very high Coulomb densities, around 10 to the higher than 10 to the 25, where you have the dead zones, which are zones where the magnetic field is decoupled and cannot produce any dynamic effect on the gas. Also, there's a current debate if the MRI is really occurring. The magnetorotational instability is the source of viscosity in the disks, and that is able to transport angular momentum outwards and mass inwards, because the levels of turbulence in the lines of the disks is not high enough. And the other possibility is that you don't have any magnetorotational instability, but the transport of angular momentum and mass is done by the torque due to disk winds. And here I show simulations of Bai and Gressel, although they have very high values of the beta parameter, the pressure of the gas divided by the pressure of the magnetic field. And this could be lower, like recent simulations of two have shown. So this is my summary. And I just want to say that the magnetic fields cannot be dragged to form a disk, because this will cause catastrophic breaking, and they won't be dragged because of all the diffusive processes that occur in the clouds and other ways of weakening the magnetic breaking. But I hope I explain how the magnetic field that is dragged to the field is going to affect the dynamics with sub-keplerian rotation and also magnetic compression, and also they are going to affect the emission of the disk. If you compare with observed sources, this emission seems to require large values of the mass-to-flux ratio in the disk. And of course, we are waiting to have Zeeman measurements of the CN molecule with the ALMA interferometer to finally know the level of disk magnetization and to be able to test the models that I just talked about. Thank you very much.
Great, thank you. So we have time for questions and discussion. So raise your hand in Zoom or in the various rooms, and let me know if you would like to ask a question. Maybe I can start then.
Jonathan, do you want me to stop sharing?
I think you can keep the slides on for the moment. It may help.
Okay.
So you showed that the emission profiles of disks depend on the mass-to-flux ratio. In those models, though, are you assuming something for the disk winds or energy carried by the disk wind? That's, I guess, my first question. And so perhaps you could answer that first, and then I have a follow-up.
These models, these models of that I just showed you of the vertical structure do not include the disk winds. But I must say that the radial models of Xu et al. Do allow the ejection of these winds, because these radial models, maybe I can show here, these radial models, in these radial models, the inclination of the magnetic field lines with respect to the perpendicular to the disk is enough to allow the magnetocentrifugal ejection of these winds. The condition of they have to have an angle larger than 30 degrees. So yes, these models, these radial models, allow the ejection of these winds, but the models of vertical structure assume a steady state, and they do not include.
But it was more, launching a disk wind takes energy, so that kinetic energy flux, is accretion powered, so there's less accretion heating for your disk emission. So that is that included yet in those kinds of models?
No. This is assuming that all the accretion is due to some viscosity that is produced by the MRI, and so it's not including the effect of a disk wind.
So if it was included, then the disks would be cooler, have less emission, I guess. And what would be the implication for the inferred mass-to-flux?
Well, it's unclear that they would be really cooler, because, as I said before, you need high resistivities to allow the wind to blow. Because the disk is sub-keplerian, you have two options. Either the wind is warm to have enough temperature to go up enough and then flow out, or the wind, or you need higher resistivities. And if you have higher resistivities, you have more heating.
Does that also go for magnetic pressure driven wind? You don't need those things then, do you?
So Boylanka is asking if magnetic pressure driven winds would be okay in that sense.
You want to drive winds by magnetic pressure, not by the magnetocentrifugal mechanism?
Well, I think the consensus now from the models of Bai and Lusur is that there is some sort of combination between magnetocentrifugal effects and magnetic pressure effects.
Yeah, I think yeah, you are right. These are not these models that I'm talking about here are not considering the winds. They are not considering the dynamical effect of doing it either by diffusion or magnetic pressure. But I have to say that the models of Bai have very large ratio of beta, which means the thermal to magnetic pressure. In this type of models I'm talking about, the magnetic field is more important than in the models of Bai. And that's why I think all this discussion really, the bottom line is what is the level of this magnetization. I think I put it here. You see these models where the ambipolar diffusion quenches the MRI, and the magnetic the wind is carrying the angular momentum outwards at the mass accretion, producing the mass accretion into the star, have betas of 10 to the 4 to 10 to the 5. So that's quite large, no? And this is something that can only be tested if you have measurements of the magnetic field in the disk.
Well, my follow-up question, in addition to the emission profiles, surely we can get some useful information from the kinematics as well then. So if we had, and we must have very good kinematic information. I mean, people are constraining the level of turbulence in disks.
Yes,
So are there models which combine the prediction of emission profiles, but also of kinematic profiles?
um, mm, mm. You mean something like the line profiles, like
Right,
CO?
right. Basically, getting the rotation curve. I mean, you could you detect the deviation from Keplerian?
Well, in fact, um, in the case of a theory, Donati inferred that the rotation is sub-keplerian from the measurements that they have of the magnetic field and the velocity at this position of 0.05 AUs. But this is very sub-Keplerian because if your Orionis are objects which have very large accretion rate, like a burst of mass into the center and very high luminosity. So these are special conditions. So I think this is the only case where the sub-Keplerian rotation has been inferred. Of course, if you have something like spiral arms, you can see the deviation from Keplerian, but if you just have a position velocity diagram with the velocity, the Keplerian rotation, you have to make sure that you know very well and very precisely the mass of the central star, so you can find out if the rotation is sub-Keplerian or not. And I am not sure that this has been done.
But surely all the models you showed which present an emission profile would also have an associated kinematic profile, rotation curve. And
Yes, by a constant factor, no? I mean, they would be. They would be.
Well, yeah.
They would be modified by this factor of sub-Keplerianity. What I mean is that you can say this is my mass and this is a rotation curve and it's a little bit smaller than the Keplerian rotation. But if I want to compare that with observations, for example, in a position velocity diagram, then I think observationally the challenge is to measure the mass independently, because right now people use these Keplerian profiles to infer the mass of the central star, but you have to have an independent measurement so that you don't know if the rotation is sub-Keplerian or not, which is something like what Donati did in his paper.
Well, I was hoping it would be some different shape so that you're not so sensitive you can't just explain everything by changing the mass of the star. I mean, if you go far enough out, eventually, I mean, you have the edge of the disk and you have this transition to the pseudo disk maybe. And can you remind us how well studied that is kinematically, and what do we learn in fact from the inferred disk sizes about the field strengths?
Yeah, I mean the transition, I didn't put it here. You mean the transition between the disk and the envelope or the pseudo disk? Yes, I know that they have been doing this work of trying to determine the disk sizes, which is something very important. But I'm not aware of the method they are using to disentangle or to define the radius of the disk. Sorry.
No, it's probably quite continuous and difficult to be too specific, but the kinematic profile should
change.
Should change, yeah.
Yes.
Well, yeah. So there are many experts on the call here. It'd be good. So are there questions from people here to Susanna?
Sorry?
I'm just opening up the discussion here to see if there are other questions.
I suppose I can ask a question, because you mentioned it at the end of your conclusions. We need Zeeman observations of CN towards disks. But at the same time, you also showed two observations of TW Hydra and AS209 that yielded non-detections.
Yes.
So should anything change in our observational approach, or how do you see that?
Oh, you mean why they haven't detected any signal? They just have upper limits.
Yes.
Okay, can you go to your slide on this? Because I noticed you said Butsy, Lankar, who was asking the question now. So, what did you mean by that here?
You mean these upper limits?
Yeah. Yes. You say Lankar 23. What does that? Can you remind me what that means? You have a detection. Do you claim a detection?
No, there's no claim of detection. Maybe Suzanne wants, but I think what we're referring to here is that in circular polarization observations, you of course have two sides of the disk that you see.
Yeah.
And either side of the disk, at least in the toroidal field, should be flipped according to theory. And the constraints that were derived from Fleming's and Harrison, they didn't account for this. So one result of that paper was was to account for that error.
They just cancel out.
Well, they cancel, but then they don't completely cancel out due to dust in the midplane that absorbs part of the emission from the far side of the disk. I suppose I asked the question before to Suzanne, like, well, what should we do different? Because in the paper there from 2023, we suggest a new method to get magnetic fields in this through broadening observations. So you mentioned that you can do very precise observations of the kinematics of these disks, especially TW Hydra. You can get fantastic centroids and fantastic line profiles if you have observations with good resolution. And what our hypothesis, or what we defend in that paper, is that with the very precise profiles of a molecule like CN that has multiple transitions within a band, you can compare the different lines for their breadth and for their individual proclivity to broaden under the Zeeman effect. Making that comparison can get you a magnetic field strength. It's actually what we're trying to do on actual data now. But since this is recorded, I can't say more.
No, thank you very much. In fact, yes, I should have said that just the limits, the upper limits are supposed to be higher than the ones that were reported. That's the effect that you were talking about, no? When I say Lankar plus 23, I meant to say that the upper limits need to be revised to higher values. But as you say, this other method, have you used this other method of the line width to have it? Has it been used for any specific source?
So we're in the process of making this analysis, but yeah, as I said, now since the talk is recorded, I can't say more.
Okay. We'll have to invite you later for a talk.
Well, please let me know. It would really be important to find that.
Any other questions for Susanna? So you mentioned the streamers that are coming in, feeding the disks. Can you remind us, if anything is known yet about the polarization structure of the streamers?
Well, I think the work of Pillai showed that they were magnetized, but you mean this here, no? I didn't show any streamers, observational streamers, but I think there are measurements of the mass and the velocities, and I think there are polarization measurements that show the streamers are magnetized. I mean, these streamers are, if you look at the images, they are like regions of denser gas that has a curvature and a kinematic that seems to indicate they are falling into the center. And this is obtained because now the images are spectacular. The resolution is really very good. So I think the main question is how much mass is in these streamers. Does this dominate the accretion like these models, for example, of 224? How much angular momentum they transport? I'm not aware that the observations are so precise at this moment.
I mean, often I think the kinematics of the streamers are inferred with very simple models which don't allow for magnetic pressures and so on. Simple ballistic infall is often used. We're guilty of that ourselves. So if this can be improved, it'll be great.
And according to these models, Jonathan, the lower density medium is more magnetized than the denser stream. The sheets of dense material is less, as I remember, is less magnetized.
Mm-hmm.
The velocities, if you could measure the velocities outside the streamer, inside the streamer, they should be also different.
Mm-hmm.
But I'm not sure the observations have reached this point of precision.
Mm-hmm. Okay, any other questions for Susanna? You mentioned some regime where ohmic heating dominates, and you mentioned FU Orionis, and perhaps you could comment a little bit more on this, because I guess often when we're doing disk models, at least from our side, we haven't necessarily included this ohmic heating so much. So
well, it can be important, especially it depends on, of course, on the strength of the magnetic field. I should have gotten some slides to help show the amount of
FU Orionis it's like an accretion burst, isn't it? In a high state of accretion. Yes. So I would naively have expected, viscous heating to be more important. But can you explain why it's ohmic heating in that regime?
Because you have to cross the field lines to get this accretion.
Mm-hmm.
I mean, the material can cross the field lines if you have a high enough resistivity. So if you
that's always the case in any kind of accretion, but is it when the accretion rate is very high, ohmic somehow starts to dominate?
I'm not sure right now.
Okay. Well, we can
a simple answer. I'm not sure right now, but I'll look back into it.
Yeah, we can discuss more later. Great. Any last questions? I think we're at the hour, so if not, I'll shut the recording now. And thank you again, Susanna, for a wonderful talk and discussion.
Thank you very much. I'm going to stop sharing.